Okay, so welcome to the ARCHER2 course, the Introduction to HIP. As I said, I'm James Richings. I'll be taking this morning section of the course, and then I believe and Arno here is also in the chat, which is a member of EPC staff, will be able to help with any questions you might have while the lecture material is being given or during the sort of time we've got for practical sessions. Then I believe from this afternoon onwards, my colleague Juan will be taking over to teach the remainder of the course. So this material is provided under Creative Commons, so you can reuse within the terms of that license. There's a number of partners that work together to deliver the ARCHER2 service. That is both EPCC, which I desperately need to update the logo of from this slide. That's the University of Edinburgh. Hewlett Packard Enterprises, which are the vendor partner for the service, and UKRI, members EPSRC and NERC, who fund the delivery of the service. Okay. So preparation, so this is what we're talking about now, and if people are having issues, you should all have received a request to join the project TA224. Check your junk folders, the emails haven't been sent there by accident. You'll need to log into SAFE and set up your new machine account under this project. You'll need to supply an SSH key, and you'll need to sign up to an MFA service to gain access to ARCHER2. If you have issues, please let us know as soon as possible, and specifically message Arno in the chat while this is going on. He can coordinate with people at EPCC and our service desk to make sure that your requests are progressed quickly. Okay, so brief overview of the course to get us sort of started. This course is really split up into 6 sort of sessions, morning and afternoons, for the next sort of 3 days. We cover the basics of programming using the HIP and CUDA programming model. We talk about HIP because the GPUs we're going to be using are AMD based on ARCHER2. However, the methodology and a lot of the syntax we'll be discussing is really just a clone of CUDA. So what you'll find in many cases is you can just do a find and replace for CUDA and replace it with HIP, and a lot of the functionality would work. The core thing we try to get across with this course, though, is what is a GPU? Why do we want to program it? Why do we program it the way we do? Okay. So we'll try and my main bit this morning is to try and get across some of the underlying motivations of why GPUs can often advance over CPUs. I try and understand a bit about the initial data movement processes going on between the CPU and a GPU inside a high-performance compute node. And this kind of accelerator offloading model is the key thing we're going to focus on to begin with. This may seem rather simplistic, but getting this down and understanding it in detail is really the fundamentals that drive performance and efficient use of the hardware for the remainder of the course. And it's very easy to get lost in this as the setups and what you're trying to program gets more complicated. You need to always be aware of where your data lives. It's the best thing I can really say. We'll then talk about how to write our own kernels to run code on an accelerator. I think Juan will look at that early this afternoon. And then we'll try to understand occupancy and why it's important to drive performance to GPUs. I can hear a lot of pinging going on in the background. I can't actually see the screen. Arno, is there anything that I need to look at?
No, not really. It's just questions about getting access to ARCHER2. So I know people have sent instructions beforehand by email about how to get access, and you just shared that slide. So we probably should put something in the Etherpad as well as a reminder. I'll see if I can find some references.
Ah, yes, you've reminded me I've made one initial mistake. So the other aspect of this course that I will just flag before we move too much further along is that on the initial trading course page, we have a course chat. Okay, it's beyond this session. Okay, it is this link here. It is a scratchpad space for writing any questions you might have during the course. The issue is that this session of this sort of Collaborate software we're using to host the course, the chat isn't saved anywhere. So if you've got questions you want to be answered and written down somewhere that will be maintained, especially if I'm giving a lecture and lots of questions are happening in the background, then putting them there will give us a chance to reply and have a record of it if there's stuff you think that you'd really want a more detailed response. So please write any questions you have on that Etherpad as well, as it's just sort of, it will sustain for the life of the course and we can go back and review them as we need to. Okay, let's just go back to setting up sharing. Right. Okay. So as I was saying, what else will we cover during this course? We will also look at variations on the types of memory spaces available on the GPU, and some practical examples of implementing different kernels and collections of kernels in what we'll come to describe as streams and graphs. Getting that, and what these things allow you to really do is have different parts of the GPU execute different operations in a structured way. There are different reasons to choose those particular design decisions, but this is some of the flexibility that will enable you to get good efficiency out of your hardware. Some of the example kernels we'll discuss are quite very common and simple sort of linear algebra routines, but ultimately the end of the course moves towards a example of a conjugate gradient algorithm, and we'll be implementing elements of that through the course as examples to learn things about different aspects of the language. And at the end, we can bring together a lot of these individual examples to do something useful to try and invert a matrix. It's not absolutely critical you get to the end of that exercise. It's just meant as a bit of a capstone for those interested that want to see how this might be pulled together into a single algorithm. But basically, last afternoon is dedicated to some time to working through that example and discussing how it works. Okay, so I've talked a bit about the main themes. Specific topics then are sort of performance models and graphic processors, the CUDA HIP programming model, memory management, executing kernel, performance considerations, managing memory, shared memory, constant memory, streams, graphs, device management. Hopefully by the end of this, you'll at least have a pretty solid understanding of how these elements work together to get a highly utilized and performant GPU for a particular application code, and understand where you can get documentation and information to learn more about a particular API or process. So this precise schedule is we're going to start at 10 and finish at 4 each day. We tend to organize regular breaks, so there will be a midpoint break in the morning and afternoon to make sure everyone gets a chance to stretch their legs, takes their eyes off the screen for a bit. We also have an hour for lunch between 12 and 1 each day as well. As you can see, many of the topics I've just discussed throughout this particular schedule. The schedule is on the GitHub page that I will link in a minute once we've got through this particular lecture, and you can download the course material from that GitHub to get a hold of the exercises and the other parts of the talk material. There is also a bunch of README slides that go along with some of the material I'm talking about here, along with the exercises and description of the exercises themselves. So you can use that asynchronously. It's not walled behind anything we do. If you want to come back later and look at that, it is still going to be active and available for you to take a look. Okay, so the course material, I will try and post these links in the chat in a minute so everyone can get at them. It's on the github.com epcc ed ARCHER2-GPU-course. ARCHER2 documentation is on the ARCHER2 website. There's a user guide there and some information about the specific GPUs we'll be accessing. So these are AMD MI210 GPUs. There's a bunch of documentation about how to compile and run and deal with niggles. So if you're moving away later after this course on to trying to run your own application code or develop your own code, that's where to look for help with the ARCHER2 service specifically. If you want more general documentation around how AMD HIP works, rockhamdocs.amd.com is the place to start. And then specifically, if you also want to branch out into CUDA, really there's lots of similarity between HIP and CUDA. docs.nvidia.com/CUDA is the place to start looking there. These two vendor documentations are very long and sometimes quite detailed. I think CUDA is more comprehensive, but quite technical. And sometimes a little bit fiddly to find the right pieces that you want. AMD is a little bit higher level and a bit more simplistic, but lacks some of the detail. You should not assume that these two APIs are a one-to-one mapping. CUDA very much was the leader in this. HIP has shadowed it. So where there may be functionality in CUDA, AMD may eventually support that functionality, but it is often behind. Not significantly, but NVIDIA have been the leaders in this. I link two GTC talks here. I think these are very good talks by a gentleman called Stephen Jones, who is a CUDA architect. He tends to give a CUDA sort of update talk or general introduction at every NVIDIA GTC conference. These are very nice motivational talks about why things are designed the way they are and the problems that GPUs try to solve. I try to do a very bad job of explaining some of these themes during this lecture, but if you want a sort of 40-minute talk on this by someone sort of in the know that you can look at separately, these two links are fantastic for that and really will explain why the differences between CPU and GPU are sort of, and what the motivations were in more detail. Okay. So compute performance and graphics processors is what we're really focusing on. We're really trying to use a GPU to do some form of useful compute that allows us to be more performant than a CPU node would allow us to be. There are a lot of complications that we add in order to achieve this, but ultimately it's got to be better than what we'd get out of a CPU, else we wouldn't bother going through all the extra effort. Okay, so to baseline this, we need to start off with a very simple model of performance. If we don't start here, we won't really have a good understanding of what drives the design decisions in modern processors, and then we won't really be able to effectively compare and contrast a GPU to a CPU. So a very simple view of how a computer might operate is you'd have a processor and some memory, and really there's some data movement between memory and the processor. There might be a number of factors which could be taken into consideration in a performance model. So 4 items we're going to discuss, and we'll go into more detail, are the clock speed, the rate at which we issue instructions by the processor to do our calculation, the rate at which they can happen, the memory latency, the time taken to retrieve data from memory. So that's the time to get the first bit of data. The bandwidth, the amount of data transferred in a unit of time. So that's kind of the size of the pipe. How much data can I get per second or per unit time? And parallelism. Can I replicate this basic unit? Because if I can have more basic units, I can do more calculations at the same time. That allows me to have multiple things happen at once, and therefore I can get more work done. Okay, so why have we ended up, so often it's very common, we've ended up in a parallel world. We've got multiple cores per CPU. We already see this in the CPU. Why have we ended up here? What we've seen is there's been this is a benchmarking plot of a spec C into performance on a log scale over time. So basically this is all CPU performance data. And it says we hit kind of its discontinuity. Well, actually, we've got multiple core systems, but the increase in performance is actually degraded since we made this decision. Okay, so we had this nice trend line up until about 2004, where every year the CPU would get slightly faster, and we moved to multi-core after 2004. But we're about 7 years behind that trend line of where the performance could be. And actually, we're seeing a flattening off of even this multi-core performance. Okay. So we had to transition to multi-core performance, but why? Because it doesn't seem to be beneficial in terms of just the sheer performance of a core. Is this due to the end of Moore's law? Moore's law specifically is about the number of transistors on a microchip. Okay, not about performance, it's about the transistor density. No, we've still seen more transistors go into a particular piece of hardware every year. That trend has continued. Maybe there's limitations, but every time we say there might be a limitation coming up, someone continues to make higher density chips. What is really the issue here? As a physicist, it makes me very happy that once again, thermodynamics is the pain in everyone's side, and it's really causing the issue. That original trend line we saw around a single core performance sort of going up steadily grew as clock frequency increased on an individual core. And over time, we just increased the clock frequency. Your program wouldn't have to change. You didn't have to deal with parallelism, and your performance just got better because you could just issue the same set of instructions you had previously faster at a higher rate. So if we look at this equation on the bottom left, the runtime of a program is a combination of the instructions per program, so the total amount of work we've got to do, calculations to do, the number of cycles we take to do each instruction. Now that may be going to fetch memory or whatever else, but there's some number of cycles we need to do to complete each piece of work, and the time it takes us to do each of these cycles. So if we increase clock frequency, we reduce the amount of time per cycle, and that has an impact on our runtime. So that is this, in this plot on the left, this frequency going up between about 1985 all the way up to 2005-ish. This was the single core era, clock frequency increased, and then it's kind of stopped, and we've hit this multi-core era. Why did it stop? Because what the effect was is as we increase clock frequency, the power requirements and the power density of a particular chip went up. Okay, so could you physically cool the hardware that you were using? So this power equation in the top right is power is equal to some constant times the voltage squared times the frequency. So as we increase the frequency, the power increases, and what we start to see is we get, if you can see, this is Pentium 4 in about 2004. Sorry, Pentium 4 in about 2004 timescale is getting close to the power density of a nuclear reactor. It's well above the power density of a cooking hot plate. It is not reasonable to be able to expect to cool something like that at the correct rate, and that is a serious consideration, is the cooling of hardware in a high-performance computer. So we needed a different approach. We couldn't just keep increasing the clock frequency to get better performance out of our software. Okay. So to combine that all together into one plot, we continue to see thousands of the transistor density go up, have done for the last 20 years. What we have seen, though, is the single thread performance to kind of tail off. We've not seen improvement in single thread performance. This is because the frequency has had to plateau to keep the total power of the processor stable to a point which we can cool, but the number of logical cores has increased. So this great uplift. Now we have hundreds of cores per CPU, whereas when I first experienced interaction with a computer, we had one. So to summarize, clock speed determines the fundamental rate of processing instructions and hence the processing of data. Historically, increases in CPU performance have been related to increasing clock speed. However, owing to power constraints, modern processors have a clock speed of around 2 to 3 gigahertz. So without some unseen fundamental breakthrough, it's not expected that the fundamental speed, the frequency will increase significantly in the future. If anything, you see on this plot on the right, the frequencies kind of drop down a little bit as people have optimized. Okay, so first little exercise after that kind of discussion is on memory latency. So memory latency is a serious concern it may take hundreds or thousands of clock cells from a standing start to retrieve a piece of data from memory to the processor, where it can be held and operated on a register. CPUs mitigate this by having caches, memory that is closer to the processor and hereby reduce the access time. They have many cache layers to minimize latency for data access, okay? So they can pipeline this into different layers of caches based on access or frequency of access. This allows to minimize latency, and that can help to improve performance for CPU. So everyone gets a bit of a handle on this concept. Log into ARCHER2, and on the login node, run lscpu and take a look at what the cache hierarchy looks like. What's the size of the caches, how many layers there are, and try and get this information out. You could also compare this to what you'd run if you run this on your laptop or the computer you're at, Linux terminal, and see the types of values you receive. And if people can post those in the chat and tell me what you kind of see from ARCHER2, that would be really good. So quick break and just do a quick exercise.
So James,
Sorry,
I was just going.
Sharing.
Sorry,
Yep.
I was just going to comment on the situation with regards to accessing ARCHER2, because I said in the chat that instructions for getting access will have been sent by email beforehand. That's the old process. The new process is quite streamlined. So a machine login account on ARCHER2 was automatically created for all users who've registered for the training course. And all you need to do, if you haven't already done it, would be to add your SSH key and set up your MFA. So I will post the link to the instructions to do so in the chat.
Brilliant. Apologies, that's my misunderstanding of the change in processor. Hopefully, this is relatively quick, and we can help people specifically if there are issues by speaking to our colleagues on the help desk. So please let us know if you're having trouble getting access. But the first little exercise, I'll just post it in the chat so it's also there for everyone else, because I know I've got it off my screen. Yeah, is to look at. Yeah, that'd be a good idea. Could you put the login detail link in the Scratchpad? Let's log into ARCHER2. Right. Yeah. Okay. Katerina, the information of how to log into ARCHER2, Arno has put on the Scratchpad, which you can find here. Machine account would have already been generated for people, and detail on how to get access should be on here. So there's a specific link called training registration. For those, those who've got the information from ARCHER2, yeah, exactly. You should see something like an L1 with sort of two D and I, which have got 2 4 meg level 1 caches, an L2 cache of 64 meg, and a L3 cache of half a gig. Yes, it's L, not I. It's LSCPU. Sorry. Okay, good. So the point of this is what does an instance represent? I will have to check because I can't remember off the top of my head. Probably how it's divided up. It's probably total cache of 512, but it's probably divided up into sub blocks. So you've got larger blocks. I don't want to go too much into the detail of this because it's really, we get into design of CPU architecture in some detail. But I think it's that. The point of looking at this is to understand that it's really into this point around cache hierarchy. And the structures that have been chosen in CPU design try and have these multiple layers to minimize this latency throughput issue. Whereas that is not necessarily what we'd want from a GPU system. Let's try that. Can you now actually see my slides again? Oh no, check, just quickly checking.
Yes.
Brilliant. Right, I should be able to move off this and keep you guys looking at the slides this time. Fine. So that's just meant to be a quick exercise. I don't want to dwell too long on that. It's just a quick thing to try and understand. The other thing we might care about in terms of hardware design is memory bandwidth. So CPUs generally have commodity DRAM, dynamic random access memory, while the overall size of the memory can often be of order around 100 gigabytes. Modern HPC hardware is getting up towards a terabyte per node, but still order of 100 gigabytes is sensible. The exact size is a cost sort of money decision about how much you can afford, because especially at the moment it's exceedingly expensive. You can blame AI for that one if you so choose to. Similarly, the maximum memory bandwidth is limited to hundreds of gigabits per second, sort of for commodity hardware. The key thing to remember is that many real applications are limited by memory bandwidth, not their ability to do operations. The data movement, the rate of data movement, is usually the performance consideration of that is the key limiter. So what we often describe this as is some form of roofline plot, where we can plot the two limitations due to the hardware: the peak flops, the peak rate at which operations can occur, and bandwidth, which is the rate at which data can be moved. You can then plot your particular applications or kernel or whatever aspect of your applications in arithmetic intensity on this plot to understand if you're in a memory bandwidth bound region or you're bound by flops. Almost always you're bound by memory bandwidth. So for applications, memory bandwidth is often the critical consideration for design, especially in scientific applications. That might help to inform what we might want to design specialized hardware around, or to choose specialized hardware for doing scientific workloads. The fourth item we have discussed here is parallelism. While it's not possible to increase the clock speed anymore based on this power-related issues, we could try to add more processing units, more cores, replicate this individual unit, and now we see many CPUs have tens or hundreds of cores. On ARCHER2, it's 128 cores per node, 64 cores per CPU. You can use the information you had from LSCPU to look at this and check on ARCHER2 and compare to your own device. I won't pause for us to do that right now, but do it at the moment. On your own local machine, you're quite used to now laptops having 8 to 12 to 16 cores CPUs quite commonly. If you've got a particularly beefy workstation, it could be even more, but it's often you'll get 8 cores. That said, graphics processors are a different organization of the same fundamental components. They are still bound by these performance considerations, but they try to solve them in a different way. So the design has been driven by commercial interest, really gaming for its earlier time. They have many, many processing cores, and this is really to process individual pixels on a screen. Okay, the pixels don't necessarily depend on their neighbors, so I can do the rendering by processing whole lines of a screen or chunks of screen all in one go. I don't need to worry about data dependencies between them. Okay, there's no, if the pixel to the left of me is this, then do this necessarily. I can just choose and calculate the color for my particular pixel and do that all independently. They're subject to the same considerations as discussed above. The hardware design choices taken to resolve these considerations and limitations around power and the rest have been specifically related to this parallel pixel rendering problem. This is a trivially parallel problem. I don't have dependencies between pixels. Clock speeds in GPUs have historically lagged behind CPUs. They're usually around 1.4 up to 1.82 sort of gigahertz. So systematically about a gigahertz slower than a CPU. The memory latency has not gone away, but the mechanism they use to mitigate this is they allow very fast switching between parallel tasks. They do not try to minimize latency, they try to hide it. Okay, they try to fill in the idle times, and they're very effective at doing this. GPUs also contain typically high bandwidth memory. So this is a relatively small capacity. It's gone up a lot though. It's usually in the order of tens of gigabytes, but more modern hardware for this sort of generation is just about breaching the 100 gigabyte limit. But it has a huge memory bandwidth capacity on this memory. This is one of the reasons it's so expensive. It's optimized for bandwidth. So you'll get order of thousands of gigabits per second memory bandwidth on the GPU, which gives a much better balance of data supply for data processing. So you've got more but slower cores, but you've got a much bigger pipe to give them data. And if getting them data is the key performance consideration, then that's a much might be a very valuable design decision for science and other applications. Said about independent pixels. Right, so hardware sort of organization and sort of some nomenclature for you. I'll try and keep the level of new terms and sort of overlapping terms to a minimum, but there are some new terminology we need to get straight, and they also have different names depending on the vendor, which is really unhelpful. So cores on an AMD GPU are organized into units referred to as compute units. Okay. Each compute unit contains several smaller processors called stream processors. They are processes that are responsible for carrying out mathematical operations that are required for a task, such as rendering graphics, encoding video, performing scientific calculation. So an individual stream processor is something that's going to execute your instructions, but they do not operate independently like you'd expect on a CPU. You would give a set of stream processors a task which they will all do together. They will do it on different data, but they will all do the same task. This is a really important concept that I will reiterate as much as possible to get it clear. So each AMD MI210 accelerator present in ARCHER2 that you'll be getting access to for this course has 104 compute units. Each compute unit houses 64 stream processors, resulting in a total of 6,656 stream processors to work together on a particular problem. So you can see now you've got an order of magnitude more processor cores available to you than you do in a CPU node on ARCHER2, but you've also got a much improved amount of memory bandwidth as well. So a more detailed insight into the processor itself is given on this link here. So AMD.com technologies CDNA. I can discuss through this jargon and some other terms for this particular hardware. This is also presented on the ARCHER2 documentation as well. For NVIDIA, this picture is essentially the same. The words used to describe this are different. So a compute unit in NVIDIA parlance is streaming multiprocessor, which is very annoying because in AMD, a stream processor turns into a CUDA core in NVIDIA language. So there's often confusion between stream processor and streaming multiprocessor. I will try to stick to AMD's language. I think it's much more instructive and clearer. We'll come on to this in more detail, but you'll often hear things like wavefronts and warps referred to. These are groups of these stream processes that execute together on the same instruction. Warp actually comes from some definitions and terminology in weaving, which is as in like loom weaving, is where warp comes from as a word. It actually is quite interesting and useful to look at some of those sort of explanations for how you would deal with a loom, because it gives a sort of a practical and physical representation of what's actually happening on the GPU, which is always quite funny to me. I remember it. We also have working groups in AMD parlance and blocks in NVIDIA parlance. I'll explain those in more detail as we go, of course. Okay. So compute units / stream multiprocessors. What do they kind of look like? We might have a number of elements. So this is the data for a NVIDIA A100 GPU. So it might have a max number of threads it can keep track of, threads of execution it can keep track of in a stream multiprocessor. Maximum number of blocks that it's going to deal with is 32. Total number of registers, okay, shared memory pool sizes. They all have their own bit of memory that's dedicated to them. They have a number of threads that will operate on a particular warp, the number of different warps that can be active at any one time, and then you'll have information about the number of types of cores available to them. They do have caches, and they have a rate of, but they're relatively small caches. So if you think compared to what we were seeing for a CPU in the ARCHER2 documentation, we had 4 megs write down per core, but here we only have 128 kilobytes cache size for an SM, for a computer. So those ratios are a bit different here. And we have some bandwidth about how the rate we can get data in, and the clock speed is relatively slow. It's about half the speed of a CPU clock speed. Now, these numbers are a couple of years old now, but they're very indicative of the type of things you'll see in modern compute units across both vendors. So the sort of more detailed schematic diagram, and this is an AMD diagram that I have borrowed from some of their documentation, gives you a more detailed sort of set of instructions. But the key point here is that each of these grayer blocks is a compute unit. You have a number of these. I think we said we had 104 for the particular GPU you guys are going to access. We have a number of arithmetic logic units, so on and so forth. These make up the individual streaming processes within the sentence here. A little dot. I've got a pen. Let's point it. Okay. These are the individual little computer streaming processes. We have some local shared data that's held by a compute unit. We also have a separate constant cache, which is shared by everyone. Then there's some external caches and some instruction caches. And then there is the main memory of the GPU. So all these elements are organized slightly different to the CPU. It's really what I'm trying to get here. It's quite instructive to look at this diagram in detail in your own time. It's included in these slides. Now, can I not move forward? Okay. However, when we interact with a particular GPU node, like we will do on ARCHER2, we don't just have a GPU in isolation. It is attached to a CPU. GPU is an accelerator. It does not replace the CPU's function within the node. What we end up with a picture, which is what's called a host and device model. A GPU is hosted by a CPU node. By a CPU. The CPU is responsible for orchestrating the activity on the GPU. So that's why you get this concept of a host and a device, or a host and an accelerator. Modern configurations see a host or multi-core CPU host 4 or 8 GPU devices. That's very common in modern node architectures. And what you can see from this diagram is I've tried to keep the memory bandwidth figures. Now, these are a little bit out of date, but they're not wholly incorrect for what you might actively interact with. This also assumes that we haven't got some fancy hardware where there's like a grasshopper or some other thing more complicated. We're trying to get across the key limitation and bottlenecks we often see with these systems. So the total memory on a CPU side may be order of 100 gigabytes. The bandwidth may be of a similar order. The memory transfer from the CPU to the GPU may be of order tens of gigabytes. The memory that sits on the GPU node may be ordered tens of gigabytes, but the memory bandwidth between the GPU and its memory may be order of 1,000 gigabits per second. So massive memory bandwidth on a very small pool. All of these things give us indications of how we need to think about the programming model for a particular application and what we need to do. We need to minimize communication between the CPU side, the host side, and the GPU side, the device side, in order to get good performance, because that is a slow loop. We need to keep as much of the operations we can on the GPU because there's lots of bandwidth, and we need to reuse that memory as much as possible so we don't induce transfers that we don't intend. So obviously it's not quite as simple as that, and a given GPU node is a bit more complicated. An AMD 10 GPU on ARCHER2 has the following sort of diagram. There's 4 GPUs per node. There is 4 nodes on the system in total. Each node has 4 GPUs. They have direct high-speed links between the individual GPUs. And then there is separately connections from the GPUs down to the CPU and also out over the network. We're not going to really talk about inter-node communications between GPUs, but that is something we can do. There are no GPUs on the ARCHER2 login nodes, so you need to be careful about how you're compiling sort of automatic things when get detected. Some instructions we'll go through about how to do that effectively. And we submit jobs into a queue. So these nodes are in the background. We need to run a Slurm job to get them to run. And we'll have some specific configuration to make sure you get access to them through your account on ARCHER2. So that schedule configuration to submit from the ARCHER2 login node to get access to the GPU node, you need to add to your job script a number of GPUs you require. So you have to provide a hash sbatch minus GPUs equals n option. For the most part, we'll just be using 1. You don't need to specify the number of CPU cores or the amount of memory. CPU cores and memory assigned pro rata. So if the CPU has 20 cores and there's 4 GPUs, if you ask for 1 GPU, you get 5 CPU cores. And you get the same, like if you've got 128 gigs of memory, you get an equal fraction of that. So 32 gigs. So actually, the correct numbers are you get 8 CPU cores and you get 128 gigs per memory per GPU requested on the ARCHER2 nodes. None of the examples we give here are going to get anywhere near that capacity. But if you do start to look at your own applications after the course, those are the current limitations. We have 2 types of access. We have shared GPU -shared, which means you get a fraction of a node, or you get GPU exclusive, where you hold the whole node. We'll be using GPU shared because we'll be using very small pieces of code, and that allows us to get a large number of people onto the system to do their testing. So please remember to use GPU shared through these examples. If you want wider understanding of the GPU landscape that exists out there, here I've provided a number of links here to different hardware. There are all sorts of wonderful, fancy ways to deal with some of these hardware and data transfer limitations that people are coming up with. I try not to go into them in too much detail because the main thing we need to get across in the course is around data transfer and speeds and understanding how to do this. When we come on to performance, we really care about the speed of things like that. Another important consideration is that while we're going to talk about HIP and CUDA, this sits, and this are these sort of kernel approaches, we're going to talk about HIP, but it's going to be related very easily to CUDA. These are called kernel approaches. There is a wider landscape of approaches to GPU programming, and there's basically a trade-off between portability and the level of control you have on what the hardware does. This course focuses on HIP, and it's related to CUDA library, provide you lots of control, but the portability is very, very poor because it's really designed to program for a particular vendor. Other solutions like OpenMP offloading, which there's a separate ARCHER2 course for, allow for much more portability, but may not have all the features. So it doesn't support things like CUDA graphs, for example, currently. So does that allow you the fine-grained control you need to really get the most out of the hardware you're using? Your choice, and there's a bunch of intermediate frameworks here. So COCOS and Raja, developed by US National Labs in their pursuit of performant code, C++ base, and allows you to port between different hardware targets. SYCL has got an open source version, but was supporting, it was used by Intel to support a lot of their GPU work initially. However, they are no longer pursuing that, as far as we're aware, as a standard, and I think recently dissolved from the companies in their organization related to that. There is still some open source efforts to use SYCL. This paper is from a couple of years ago now, but is a good understanding of the level of support as well, depending on the hardware, the language you're using, and the different implementation of these sort of programming models. And as you can see, there's not the same level of support. It's not as ubiquitous as we see in the CPU world, where our compiler usually supports most of the CPU types we might come across of, even if maybe the support for everything isn't there. Here, it's much more patchy. So do be aware and keep this in mind when you're thinking about how you're designing your programs and which languages you're going to approach in future. Yeah, so this is a paper by Andreas Hurd for 2023. The link here to the archive is on the bottom right. It's a very interesting paper. Do take a look. I know I've just had a question. I'm just going to try and get to the end of this session really quickly, and then I can go off this and not cause me to lose sight of everything. Right. How can I help? What do the numbers represent in terms of in the references in the little table? Yeah, accuracy. Oh, I think their references are referring to a particular paper or study that's been done. This is kind of like a meta-analysis. So someone's trying to bring together a lot of insight. It could be scoring in terms of, I think it's either the links or it's trying to link to a discussion or score related to its portability, effectively. I'm trying to think if it's actually on this page. It could be a ranking, actually. But you're right, you say some are doubled up. Yeah. I'd go and read the paper to find out. So how we do for time? We're a little bit over. Okay, I'll try and wrap up this lecture so we can have a brief break. This is quite complicated to program for GPUs. It's been about 23 years, sort of starting scientific computing to being ubiquitous and something we're using at scale in commercial operation. So the first programming models for this were done in 2002 to try and use shader libraries to program for a particular computational workflow. Okay. I think we're going to take a brief break, and then I'm going to come back to the HIP and CUDA programming model. So everyone gets 2 seconds to get a cup of tea and have a bathroom break. if we come back in 10 minutes, is that okay with everyone? Does anyone have any objections to doing that? Just very aware I've been talking for an hour and probably everyone needs to let their brains process. Okay, great. So we'll come back at 1:15. The 8 NUMA nodes question is interesting. Yeah, it's a configuration option. There is a tuning document that AMD provide, and they have 4 probably different modes. It's NSPC 1, 2, and 4, and it's per CPU. So the way ARCHER2 is configured is NSPC 4. So you have 4 per socket, and that gives you the total of 8 NUMA nodes on a particular ARCHER2 node. The effect is how are those caches shared between different cores? Because what you really do on an ARCHER2 CPU is you have 4 blocks of cores, sub-dies. This makes the process for production very efficient and reduces the cost of the hardware, opposed to generating one monolithic die in one single pass. Because if you have any defects in that big monolithic die, you have to throw it away. But what it leads to is a sort of a communication pan on the chip as a whole. So your choice for this particular NUMA regioning setup can affect performance. So it's something we have to optimize. It's not something you as a user can choose. Unfortunately, it requires a node reboot. So performance analysis has been done about which is the best setting based on the software on the service. Okay, I said we get going when back. If those who if everyone could just give me some sense that you have returned, so I don't just start speaking to an empty room. Just put your thumb up in chat. Just say hi. That'd be great. Fantastic. That's at least 5 people. Good. Okay, you're alive. Fantastic. So let's get going and finish this section. So try to give a bit of an overview of the motivations of why we might design a GPU the way we do and why it could have performance benefits for a particular device that we're sort of for a particular code we're trying to run. Now let's talk a bit about the programming model to utilize that device itself. Okay, so the application programmer does not want to worry about the deep composition of cores, these compute units in the hardware. We really want to use an abstraction. We should care about it and the details of it when we really want to go after performance, if we want to make sure we're making sensible choices about certain sizes of things and the choices we use to decompose our problems. But we ideally want an abstraction that works anyway. Really, we want this to work performantly regardless of some of these choices, but that's never true. We really want it to be reasonably good without having to make a lot of detailed choices. What we really want, though, is a way of describing the problem in terms of a hierarchical organization of threads, because that's really what we're going to do to operate on our particular problem. So the way to start thinking about this, if we have a one-dimensional problem, like an array, we can assign individual elements to threads, okay? So if I've got an array that I'm going to do the same operation on, or each individual data element, there's no dependency there. They can all act and be updated independently. So I just increment every single element of an array by 1. That can all happen at the same time, as long as everyone writes back to the same location. So there's no memory overwriting or race condition problem. That's fine. So we can assign individual elements to different threads in this, like we see in this diagram. So thread 0 gets array element 0, thread 1 gets array element 1, and so on. So I briefly mentioned the word working groups earlier, or blocks in NVIDIA language. A working group is a collection of work items or threads scheduled to run on a compute unit. In our one-dimensional picture, we would have the following. We'd have block 0 has threads 0 to thread n. Block 1 has thread 0, another set of thread 0 to thread n. Block 2 has a third set, thread 0 to thread n. A wave, and that was how you divide up a very big array, maybe to work on. You wouldn't have to have you couldn't necessarily have a humongous block. You might want to have smaller but multiple blocks to deal with that array. What you're really saying is these blocks are also independent. We know the threads are independent, these blocks are independent. And what this allows the GPU to do behind the scenes is allocate work, the operation, and get those different blocks to run independently. This allows to hide some of the data fetching costs underneath, because all these blocks can be scheduled however the GPU chooses. Blocks may be of different sizes. So it basically starts playing a big game of Tetris to do the calculation. And that's good. You want the GPU to deal with the Tetris and do something sensible with it. We also have another term that's important, which is wavefront. I didn't really go into in detail earlier. A wavefront is a subset of a particular work group or a block in NVIDIA words. And it's designed to execute on a single instruction multiple data unit, right? So this is a particular compute unit has 32 threads. It's going to execute a particular wavefront on that compute unit, but there may be more elements to the particular block that are going to execute on that hardware next. So wavefronts might commonly consist in AMD hardware of 64 threads. That's because the number of threads one of these streaming multiprocessors have, or one of these compute units has. So wavefronts are mapped to compute units for execution by the hardware scheduler. Developers typically select the number of wavefronts or working groups, often based on the problem size. Nothing. There is no difference between SIMT and SIMD here. I am just using single data multiple instruction single instruction multiple data, because I do not think the distinction helps significantly. So we often hear SIMT as single instruction multiple thread. Ideally, you still wish each thread to have a different piece of data to work on. It's not necessarily true, but I mean interchangeably in what I'm describing. And this is really the point. A single instruction should be run on multiple threads in the GPU. That's how they get the performance benefit. Okay. How we decide to divide up our threads over the work we've got it to do is our choice as a programmer, and we can make sensible about decisions on that. That's the model that we're going to use so that the GPU can schedule work effectively. This model quickly expands to 2 dimensions. And you can start to very much see the why this was logical for trying to update pixels on the screen. If I can divide my screen up into useful blocks, I can have them all execute, and they're all independent. They can all execute independently, and I can update my screen quicker. I get a better refresh rate, I get better graphics, I get happy gamers. We can take advantage of this to do computation for other, maybe more useful things, for playing games, depending on your particular hobbies. So it's natural to have a 2-dimensional picture. We can then arrange work groups, blocks, into a grid. Okay, so you have these 3 levels. You have threads, blocks, and a grid. We can keep going and extend this to 3 dimensions as well, and that's true in both CUDA and HIP. It just gets challenging to visualize in a presentation, so we'll stay to 2 dimensions. So I'll actually say what HIP stands for. It's Heterogeneous Compute Interface for portability. It's one of these annoying compound terminologies that miss out half the words. It doesn't really matter. It's importantly a runtime API, though, same as CUDA. It's a kernel language implemented in C++. The tool enables developers to create applications that are portable across AMD accelerators and provides some portability to CUDA as well. You may not choose to use it to port to CUDA because the developers are AMD themselves, they are a competitor of NVIDIA. They won't necessarily keep things identical. They're not in the game of supporting all the CUDA functionality, but they do want to make it easy for people who have maybe written code in CUDA to be able to get to run on AMD GPUs as well. So you can think about it that it's a support is modeled in that way. It's a way to try and be accessible to people who already use CUDA. So importantly, HIP has two distinct types of source code in the functions and routines we will write. Host code, and essentially the CPU executes the host code. This code has typical C++ syntax, incorporates standard features, is the entry point for execution of the main function, utilizing the HIP API. The host code facilitates tasks such as generating device buffers, managing data transfers between the host and device, and initiating the execution of device code. The device, which is typically the GPU, executes the device code. It utilizes a C-like syntax where the kernels are used to launch device execution. You write a kernel, you bundle it up in some call, it is then launched, but it is then executed or committed to the device set of work by the CPU in a host side HIP call. That is then available to be executed on the device side at a later date by being queued into a stream for execution on the device. There is an asynchronous process going on here. We don't necessarily sit on the host side waiting for the GPU to finish its work. We can be getting on with other useful work on the CPU while we wait for the GPU to complete the particular job we've just given it in the kernel. And this is a really important concept to get across when we're programming, that there are two types of code, there's two types of execution going on, and we need to think about synchronization in terms of when we start to do the next step in our program. Okay. Compilation on ARCHER2 more generally in AMD, but on ARCHER2 specifically, I'll cover now. So HIP-CC is a compiler driver utility that calls the AMD LLVM compiler. If you were trying to compile for CUDA, you'd use MVCC, but we're going to use HIP-CC as our compiler here. It includes the AMD ROCm software stack, so that can be linked. HIP compiles both HIP code for GPU execution and non-HIP code for CPU execution, defaulting to the AMD LLVM, AMD Clang, or C or C++ compiler. Other host-side compilers can be used for the non-HIP code, and the object files can be linked separately. You can play around with the settings for this to understand how HIP-CC provides you capability. Look at the help information of HIP-CC. There's lots of options you can play around with. To use it, we call HIP-CC -x HIP that says go through this file and find all the HIP related code and compile that before you then run the host side compiler. We'll have some code we're going to pass through as code.cpp. We don't have a particular file yet, this is just an example. So the -x HIP is the key bit here. This is the bit that instructs HIP-CC to interpret the code as HIP specific code. This saves us in our example from having to have all the HIP code in separate .hip files and make it all separated out. The only reason you do this here is because the examples are relatively small and we're trying to keep everything relatively easy to look at in a single file or two files and not make it an exercise in complicated IDEs and other challenges that might make learning this more complicated. And you can see exactly what HIP-CC passes to the compiler by running the -- verbose option when you compile a code. So you can see all the additional flags that get sent in and understand exactly what the compile chain is doing. But you have this concept of multiple passes. There's going to be a pass that deals with all the device side code that gets compiled, and then there's going to be a pass that deals with all the host side code that's getting compiled. On the right, I've got some examples of the compiler and the programming environments and the compilers that are related on ARCHER2, and the different things you'd have to load in to get this to work. We'll give some specific instructions for this for doing compilation on ARCHER2, but this is in the ARCHER2 documentation as well if you're going beyond this particular course and wanting more information. Another important aspect of compiling GPU code is compute capabilities. The idea here being that as different versions of GPUs have been developed, the fundamentals that make up a compute unit has changed. The instruction sets, the memory sizes, and all the other bits that are on the device get updated with different generations. So you will need to supply the compiler with information about the specific hardware you're targeting and the architecture we should be targeting, so we can do optimizations for you. If you do not provide this, the compiler will try to make some guesses, or it will not target the particular hardware you're trying to run on, and you will get issues when you try to execute the code. It's best practice to supply the specific offload architecture which you want to use. So in our case, this will be GFX 90A, and you'll provide minus offload architecture to the compiler when you're compiling examples. This will allow it to run on a subset of the AMD GPUs that are available in the world. So you can see here at the bottom in this table on the right, I know it's a little bit small, but GFX 90A would allow you to target both AMD MI210s, MI250s, and MI250X accelerators. If you had previous generations, you'd need a different code here. NVIDIA has a very similar process. You have to find something called a gen code as well. Otherwise, what in the NVIDIA case will happen is that it will try to compile for every possible hardware or select set of target hardware. And this can increase the size of your binary significantly. It also increases your compilation time, because effectively it's going to compile for multiple copies for different devices. So do try and specify this offload architecture. Okay. I mentioned portability and parsing, but a little bit more formal text on this. So CUDA has been developed by NVIDIA since around 2005. AMD has been rather late to the party, develops HIP, which tends to shadow CUDA. Luckily, AMD were rather sensible and kind of decided to make their API look the same, because otherwise you would have two different approaches to the same problem, which is what we see with this large space of different methodologies for programming for GPUs. This makes it harder for you as the programmer to keep track of how to do the same types of operations, and it's not very good for your productivity. So you might often see just the replacement of CUDA and HIP and CUDA all over the place. That could be a very easy way, very simple codes, just big, so portable, but there isn't really a formal mechanism for targeting, doing this translation outside of some scripts called Hipify that AMD supplied to allow to convert from CUDA to HIP. And also the HIP compiler can try and interpret CUDA code itself. But if you're using more advanced features in your CUDA code, then you may have issues that those features are not supported by HIP. So you just need to be careful about these. Auto translators are a good starting point. They are not magic, however. They will introduce bugs and errors that you'd expect with any automatic translation. So be careful using them. Okay. So I've already just said about Hipify. There's some documentation here that will link to how to use some of this. It's a good starting point, but won't necessarily be perfect. It definitely will not be performant. So a case where you may have issues is that you could automatically translate between the two languages, but the choices of block sizes and number of threads and so on and so forth that will really impact performance will be different between the two different architectures. So you'd still need to go back and tweak those to get the performance out of the hardware you want. That's something you do need to consider by using an automatic translation tool, because you could end up very easily with very inefficient GPU code, especially if you choose or make decisions that don't give good block sizes and therefore good utilization of the hardware. Okay, this is to summarize this section. The goal for the programmer is to describe the problem in an abstraction of grids and blocks and threads when we're programming for a particular problem. The hardware is then free to schedule this work as it sees fit. This is the basis of a scalable parallelism for the architecture. And then the very latest documentation on HIP can be found here, and the documentation that's most relevant for ARCHER2 can be found at the bottom. Okie dokie. Before I move on any further, are there any questions at this stage that anyone has? I know I've talked about a lot of technical detail. I'm really in this stage trying to set the scene so that it's clear why we've motivated this approach. You should be able to, yes. Whether vast, in principle, yes. Is there the compiler support you need? That is a question you would have to try and debate. There's some documentation about the level of OpenACC support and which programming environment to use in the ARCHER2 documentation. And we can try and answer any questions around this as well. So I know me and Arno had some fun trying to figure this all out when we got access to this hardware originally. We will try and remember what we found out. Try to document. Okay, so if there's nothing immediately, I will then move on to the next section. I'm running up to lunch and leave you guys with an exercise to start thinking about, but we'll have some little bit of time after lunch when we'll look at when we come back. So just trying my ducks in a row here. That coming through okay for everyone. You should be able to see here a new screen with HIP programming model on it. Brilliant. Okay, so I've described the programming model, but we've not really gone into detail about the syntax of it. So now we're going to start looking at some of the syntax up to a first example. We're going to start off again relatively slow. We're going to focus initially on memory. And it's simply going to feel like I labor this point endlessly, but it's the thing that gets most complicated. We have to assume there are separate address spaces for CPU and GPU memory. Those of you who may have got access or experience to more modern GPU hardware, this may no longer be true. I might have an argument with you whether that is really what's happening in terms of performance, but to give us the most general version of this model, we assume that they are separate memory spaces. Yeah, so the MI300A and the NVIDIA GH200 feature unified memory spaces. This is a single address space shared by host and device. This is unified address space, but not necessarily unified access speeds and bandwidth. That's very important, especially with the Grace Hopper. Okay. What to include, what not to include. So the standard C++ source may start with hash include hip/hip run _ runtime.h. This is usually relevant for programs to be compiled by hipcc. There is also a subset of the runtime, which is just hip_runtime_API.h. This is the C++ interface that does not need to be compiled with hipcc. So effectively, this is just a library that's being called. It doesn't actually execute anything on the device or need to know anything about the device. Data accessed by a particular kernel, a particular piece of code that sits on the device, must reside in device memory. So if I'm going to access memory I want to work on, it must already be on the GPU. This is referred to as device global memory or just global memory. I don't really like this global memory terminology because it puts across the assumption that this is accessible from anywhere. It's not the case. So I will often refer to this as device memory, but you will see global memory referred to a lot in other literature. There are different ways of managing the allocations and movement of data between host and device. We can do explicit allocations and explicit copies, or we can try and use some managed memory schemes where effectively you hand over the organization of the memory to the runtime, to HIP, and tell it to do it for you. There are performance implications to doing that and handing that over to the runtime. And it's again a balance between how much control you want for performance and how much you just want to let it do it and happy that it's managed for you. We're going to start with the explicit methodology first. We're going to look at how we would implement copies by hand. We'll also come up to the manage method later on. So memory allocation. First of all, a variable that references device memory is declared using standard C++ data type for a pointer. So here at the top of this code example, we've got a double pointer, which is called data. I'm just going to set it to null. It should probably be null pointer to be proper, but it's going to set to a null value. We are then going to allocate some data location, some region in memory on the device. To do that, we're going to call hip malloc. We're going to pass hip malloc the reference to this pointer so that on the host side, we have a reference to know where on the device this data is going to be stored. Okay, so such pointers are host pointers to device memory. The pointer lives on the host. Its value is related to the device location. This terminology and getting this straight in your mind is really important because it becomes very easy to get lost with this concept of what's on the host and what's the device. This is the CPU's reference or knowledge of, look at table 2, the memory locations on the device. Because I'm going to need this if I'm going to move data, I need to know where I'm moving data to. Question, chat. Okay, I can repeat again. Yeah, this is important to get right. So hip malloc, it returns an error code because this is a process that the function returns just an error code to say, did I get a valid piece of data, a data location on the device? I then store in the pointer data the location of that piece of memory. That piece of memory sits on the device. It may be 10 gigabytes of device storage, 10 gigabytes of GPU storage. I need to, on the host, because the CPU controls this process, to know where that data is. So later, if I want to move data from my CPU to this GPU region, I need to know where the memory is located, which I'm going to read from, and I need to know where on the device I'm going to write to. The CPU already knows about its memory and its location, so you don't need to specify that especially carefully, but we do need to give the CPU a handle on where on the device we're going to write this data to. This hip malloc call is that mechanism for controlling, for giving that reference to the CPU. Okay, so we're going to do an example on this. I'll keep referring to this a lot, and doing a few examples will help. The key thing at the end, though, is we've allocated this data on the device. We're going to do then some work, moving data to it, from it, playing around with it, updating information on the device, whatever you normally do with a computer program. Later, we on the host need to say to the device, I am now done with that region of memory I had access to, that array or what that other object was. I'm going to now tell you, because I am the host, I control what you do, GPU, free that data region. Okay, you need to explicitly do this, same as you might just do on the host, but this is a call through HIP that goes across to the device and releases that memory. So now to do memory movement. So we're assuming now we've established some data on the host. The copy of the data to and from the device is done via HIP memcopy calls. Here, I take in that data, that pointer that's from the device that I just generated with HIP malloc. I also take in some location in my host memory on my CPU called host data. It's an array of length of n, size n. Okay, it has 10 elements, 100 elements, doesn't matter. They're all doubles. So a really simple array, something you'd commonly come across. I call HIP memcopy to move the data from my host to my device. So I call this HIP memcopy, but I provide this final element, which is information about the pattern. This is called HIP memcopy kind. So you can see the full specification at the bottom, but I'll keep with the example at the bottom for now. So HIP memcopy host to device specifies the direction the memory is moved. So that means I'm going to take my data from my host and place it on my device. I will then do my operations on my device. At the moment, we're not going to do anything. We'll define in a later lecture how we might define some operations to do on the device. But we can assume that that will be the only reason we copy data to it, is to do something to that data. Later, I want to get that information back to my CPU, maybe to reduce some I/O or whatever else. I can do HIP memcopy and now do this in the reverse direction. So my kind is HIP memcopy device to host. And you can see I've reversed the order of my arguments. So you can view this as destination and source. So the destination is now back to the CPU, back to the host location from the source that was on the device. This returning location does not have to be the same place we started at. This could be another location on the host. Same thing over here. This doesn't have to be the same location. If we want the same data, then yes, it will need to be. But if we want to take from a different location, we could choose anything we wanted to do here. We can have multiple of these. A key consideration, though, is these are blocking calls. They will not finish and return until after the transfer data is complete or an error has occurred. So what this means is, because we're doing communication where the host and the device are both happening, there is a block occurring, which means execution on both sides will not continue until this transfer has completed. So on the CPU side, everything would stall until this is returned. That is not true of all calls within the HIP framework. So the full details of this setup are below, but it's destination from a source of a given size, and then we provide this kind, which is the direction of memory being copied. An important thing I brought up a couple of times is error handling. We're going to provide you during the exercises some helper routines to deal with this for you and catch errors and deal with the error codes, but you do need to be aware that this is an important consideration when calling these kernel type routines for ARCHER2. So just out of interest, who in the chat has experience with MPI, for example? Has anyone heard of MPI, used MPI? And a few people, Right, how many of you actually use your MPI error codes? That's a miracle. Someone said yes. Okay, exactly the same concept here. For those who are used to MPI, this is something that's happening asynchronously. My calls to HIP have an error code. I need to check it before I move on. I need to check whether the operation is successful or not. Okay. The other important thing here is that this error, where it's not like MPI, is this error is happening on the device. This error, if something goes wrong on the device, I know nothing about it during the execution on the CPU side unless I go probe it. So in MPI, I might have two processes that communicate, and something might happen on one of them, but that process would fall away and the program would collapse. I might have an error on my device, but that error is not getting automatically sent to the process to kill the controlling process, the CPU side. So I do need to regularly check these errors to make sure that everything is okay on the device side. No, there's not. Well, yes, we'll come on to that. It's not as complicated as unique tokens, but there are. So the question in the chat is there a unique token for each mem copy call like MPI send receive calls, where you're sending information between processes? What it will depend on the pattern of the communication. What you're more likely to have is a setup where you have multiple GPUs with one CPU, and you will have some way to number the CPU, number the GPUs with the devices you're targeting. So you might need to switch between where the mem copy is going if you've got multiple. That's a complication we'll come to in, I think, late tomorrow or the day after. The point for now is that we've got this concept of moving data from host to device, and we've also got to deal with the errors that come out of this in order to make sure that our computation is correctly progressing. And this will not throw errors like we would expect in host-side code because the GPU will just sit on the errors. We can inspect the errors by calling HIP error name and HIP error string to get more detail, but we need to do this as an active part of our code. So we provide HIP assert as a wrapper macro. Please use it around. It's not in the standard. I'm pretty sure we've provided this as a little bit of code for all the examples. This just does the probing for you, so you don't have to think about it. We omit it from all our example codes. So anytime I'm showing code in the slides, not put the HIP assert around because it makes things a bit confusing. But when you're writing the code and implementing stuff in the APIs, do use it because it will help you work out if there's problems. Yeah, it's particularly important to check the first API call of the code. This will detect if there's problems with the HIP context. So is that runtime that's dealing and monitoring the device set up correctly? We don't want it to do something weird later on. Jump in without checking these codes, especially at the start. It's good practice to do this as much as possible. Okay. Right. We've got a little bit of time before lunch. We've only got about 10 minutes. What I'm going to suggest we do then is I'm going to stop lecturing for now. I'll just talk through this exercise before we leave for lunch. Look at this exercise, read through it. The details are on the web page, and then on the GitHub. You can download the code and submit it. When we come back from lunch, Juan will be taking over this session. I will make sure he gives you sort of some time, an amount of time to go through and try this exercise after lunch. And this will take you through doing some of these initial data transfer exercises to make sure you're happy with the concept of allocating a resource on the remote device and moving data between. Okay, so I'll just talk through this and then we'll break for lunch. We've provided some source code, and this is a template for implementing a single scalar function that multiplies all the elements by a constant. I think this is, yes, this is doing what we need to do. Okay, first we should check we can compile an unaltered version of this templated code. It won't do anything, but we just want to check that our setup is correct on ARCHER2. So don't do that now, but these are the instructions to do that. I hope these are the slides. Yes, I will send the link to the GitHub page after I explain this section. These slides are actually as a README on that particular GitHub repo, but the information is all the same. To use the correct compilation environment, you've got to load some modules on ARCHER2. So we need to set our programming environment as AMD. We've got to choose Rockham as the, thanks Arno for posting that. We've got to load the Rockham module, so we've got the right underlying libraries for runtime. We're going to load Cray P Accelerator AMD GPFX 90A. This is trying to set some environment variables around the correct architecture we're going to use. And then this other one we're loading Cray P -x86-Milan is because the CPUs on the GPU nodes in ARCHER2 are slightly different. So we just need to make sure it's set. It doesn't really matter for the last one, but for completeness, we include it. Yeah. Okay. So to compile these code examples, we're going to need to provide this little compilation line. There's quite a few parameters being set here, but they're all kind of necessary. This is one thing you'll see that's different to running CPU compilation. I mean, in complicated codes, the number of elements of a compile line will get more and more complicated. We haven't tried to wrap these too much in make files so that you guys sort of can understand and get a handle on what all these bits do. But do understand these are quite complicated. So you will need all these elements to get this to compile correctly. So the first job is to compile and just see that it runs. What you should see is all this is doing is copying some data from the host to the device, checking the value, doing something to the value, and then passing it back. And then the CPU side is doing exactly the same calculation and checking that the values have been done are correct. It's really simplistic. The code's only a few tens of lines. You should be able to see what it's doing. And the idea is it will print information about the threads and the blocks and the updates that you're going to get. So the key thing, there's some documentation in the code example itself. What we'll need to do is declare and allocate the device memory, call it d_x of double type, copy the initialized host array h of x to this new location on the device dx, copy the unaltered device array back to the host into h out, and check that h out has the expected values. And then we need to release this device memory. Remember to include asserts on all your HIP calls. There is no actual kernel doing anything at the moment, so the output should just be the same as the input. We're not really doing any updates. We're just multiplying things by 1. We're not even doing that. We're literally just pass data across, pass it back. And we can check this is all window correct because we are taking data from hx to dx and from dx to h out. This should make sure that all the elements, and what you should get at the end is just some check that says all the elements are correct, and that you can see that this sort of copying is actually happening, and this is how you do this. There's a little bit of extension if you get to the end of that. Yes, you'll need to download it yourself into the copy. If I put somewhere in here, this will be in the shared location because that was not the intent. I can pass you the link to the. So Arno's passed the. I'm trying to say here. So the link Arno has shared that I think is also in the gathered pad onto the pad. Yeah, it's in the Etherpad as well. I will just go to that location now to show you what you should see and what you should be downloading. I think it's that. Yeah. So this is the GitHub page for the course. It's loading. Yeah. There's a detail about the schedule and the like here. The key thing is you're on section 2.01. there is the discussion of the slides here in detail on the exercise at the bottom that you guys can look at yourself. It's not as nice as the slides, but it's the same information. There is a make file here, which is going to help you out with all the compile information, and the exercise detail is here. Okay, so you need to update this file. There then is a submit script to submit work to the queue on ARCHER2. Yeah, it's usually just to clone the entire repository. Yeah, so the key point here is the compiler isn't going to optimize the explicit calls to move the data back and forth because it's not that smart. There is always that. This is the difference maybe between managed memory. You're telling the process what to do. You're not letting it make assumptions about optimizing that away because these are explicit calls to do the move. What we'll do after this in the next example is write a particular kernel that's going to update the values. It's going to have this very similar process, but that kernel is going to make sure things are changed on the device. But you're quite right. There's a risk, but I don't think that's going to happen here because you're doing the explicit version of the data. Okay, so we're going to stop for lunch now. When we come back at 1 o'clock, Juan is going to take over lecturing. And he will give you some time to work through this exercise. Thank you for all attending this morning, and please do get in contact if you've got any further questions, either through the Etherpad or the chat. Me and Arno, well, Arno and Juan will return at 1 o'clock. Thank you. Yeah, back up.